It's not only acoustics, it's half acoustics and half airflow, you'll be happy to hear. I know the acoustic stuff really well. I don't know the airflow stuff all that well, so we're in this a bit together. And what I'd like to do today, if you'll permit me, is tell you about a subject, natural ventilation silencers, that I became involved in, I'll tell you how, back in about 2006, and have been working on ever since, and it's not finished yet. The project has probably gone through 4 or 5 or 6 different phases. And what I would propose to do today is actually give you a bit of a historical review from beginning to the present, and also tell you what's planned to finish this off in the nearest future. What I also want to do, of course, is show you why we're doing this. And of course, the justification from it is that people were complaining about, for example, poor acoustical environments. And so the whole objective of this engineering work is to improve the health and well-being of the people using the buildings we're talking about. Some of the engineering stuff, some of you won't like or be able to relate to. I won't dwell on it, try and get the idea. If nothing else, I hope to show lots and lots of sort of nice pictures of buildings on the campus and parts of them and things like that, so I hope that's fun. Okay, so internal ventilation openings, natural ventilation openings, I should say, I guess, so internal in naturally vented buildings. What are these things, and why are we concerned about them? In particular, why do they cause acoustical problems? Well, the issue here is that in a naturally ventilated building, you do not have a mechanical system with lots of fans that are pumping and blowing the air around the building. So wind and buoyancy effects, the stack effect, are what create the pressure drops that drive the ventilation air through the room and the openings. And the pressures associated with natural ventilation systems are usually less than about 10 pascals. These are much, much less, orders of magnitude less than are generated by mechanical systems. So you must have low resistance paths that the air can flow throughout the building to supply enough ventilation air to meet various requirements. The problem, of course, is if you create big openings for air to flow through naturally, noise flows through it naturally too, sound, and that causes noise complaints because it's detrimental to the sound isolation, the amount of attenuation provided by the openings. So the overall objective of all of the work that I am talking about today then was to investigate the optimal design of silencers to be built inside these internal natural ventilation openings in order to achieve acceptable acoustical conditions, for example, speech privacy, without sacrificing the ventilation, airflow requirements. And by the way, we're talking about internal openings, not windows in the external facade of a building, internal. Okay, so have you ever seen these things? Do you know what I'm talking about? Well, if not, here's a bunch of pictures of some. Most of these are taken here at UBC. So you, of course, recognize the natural ventilation openings in all these partitions, right? If not, let me give you some assistance, okay? So there's all sorts of things, all different sizes and shapes of things, sometimes with grills in them, sometimes not, you name it. Okay, so how did this whole story start? Well, it started, as I said, back in 2006, where I, and Karen Bartlett was also involved in this, were invited by Stantec, the local green building designer, to become involved in a fairly big project which was going to evaluate from many, many different perspectives, and I was asked to look at acoustics, of course, 6 green office buildings. So very quickly, 6 green office buildings, 5 in the Lower Mainland, 1 in Toronto, as it turned out. 2 of them were naturally ventilated. And the overall objective, I'm not going into any detail here, was to evaluate these buildings and learn the lessons for design. How can we build better green buildings? So very, very, very briefly then, the methodology was involved was, first of all, there was an occupant satisfaction survey made available to the occupants of the building to find out their subjective responses to the building in various ways. You'll see some results in a minute. The tool that was used for this was an online survey developed by the Center for the Built Environment at the University of Berkeley, UC Berkeley. Also, extensive acoustical measurements. For my part of the work, the acoustics were done throughout the building. And then the results were related in order to identify good and bad places and then try and figure out why they were good or bad. And then to take all this and to try and understand what we learned from it for the design of buildings. So let me show you an occupant satisfaction survey result to start things off. Again, these are results from the Berkeley survey. You can see on the left then the different categories that people are asked to rate: general satisfaction in the building with the workplace, satisfaction in the office layout, furnishings, thermal comfort, air quality, lighting, acoustics, washrooms, cleanliness, and maintenance. And occupants are asked to rate on a Likert scale from -3 to +3. -3 is sort of maximum dissatisfaction, +3 maximum satisfaction. Possibly you could say that 0 is neutral. This shows the result then for 5 of the 6 buildings that we studied here, plus a bunch of other buildings which had already been studied by Berkeley. And there is the acoustical result that we are looking at. So you can see there's quite a lot of satisfaction, positive scores in general, with a few little exceptions. Thermal comfort people don't seem to be overly happy with thermal comfort, and similarly not very much with the acoustical quality. Okay, so at the end of this study then, what were the problems that we felt that we had identified, possibly explaining these results? Well, first of all, in different places of the building, too high noise levels, excessive reverberation, insufficient speech privacy, and insufficient sound isolation between workstations, especially in open plan type areas. Specifically in the case of the 2 buildings which were naturally ventilated, too low noise levels, no fans to generate a background noise in the building, they're too quiet, and also insufficient sound isolation of internal partitions and also external ones. Well, this was the thing that started this whole process that I'm talking about today. Hard evidence that people are concerned about the acoustical environment, and one of the reasons is that in naturally ventilated buildings, there's these internal openings which have insufficient sound isolation and lead to lots of acoustical complaints. Okay, so as I said then, the design implication that came out of this is green buildings with natural ventilation involve air transfer openings and partitions which significantly reduce sound isolation and lead to acoustical concerns. So the next thing that happened after this, the next year, 2007, one of the architects from Stantec asked me to get involved in some other projects. In particular, he wanted me to do a study on the Liu building here on the campus, which had been a Stantec building, and it's naturally ventilated. If you've ever been down West Mall, you'll know the building. There it is. One part of it anyhow, 3-story office block is the part we were interested in. There is sort of an elevation showing the natural ventilation system. And what basically happens here then is that air is brought in at a low level through vents, and it sort of diffuses along the floors, and then it flows up between the floors by these 4 ventilation stacks here, which have slots in them that allow the air to communicate between it and the floor where it's on, and it eventually exhausts out the roof. As the air flows down the corridors then, how does it get into and out of offices? Well, these office partitions, you'll see a photo in a minute, have these 45 centimeter openings all along the top of the partition separating the office from the corridor to let the air flow through. And of course that lets the noise flow through too. So we applied the Berkeley Occupant Satisfaction Survey to this building, and I'll show you the result in a minute. After I talk about this building, I'm going to talk about its next door neighbor, the Choi building, and we had occasion to do this occupant satisfaction survey for it as well. So the result is on this one. And a bunch of other buildings have been added in here too. Okay, so same thing as before, acoustical quality you can see. And now of particular interest is View and Choi, both naturally ventilated buildings side by side. And there is the acoustical quality satisfaction result. People are very dissatisfied with the acoustical environment in there. So we did an extensive study, many acoustical measurements to understand exactly why in detail and to quantify it. And we essentially found that these problems can be associated with two different sources. First of all, low sound isolation between floors of the building, between the first, second, and third floor via these ventilation shafts. Okay, so here's a picture of one of these ventilation shafts. You can see there's a hole with a grill in it in the floor ceiling slab, and then this box taking the air up, but it can go out these slots to communicate with its floor. But you know, you could talk next to one of those boxes and hear people talking 2 floors above. Bit of a problem. And then also, here's one of these partition openings between an office and the corridor. Okay, big hole. So low office corridor sound insulation due to openings in the partitions on the 2nd and 3rd floor. So we wanted to try and propose ways to fix the problem, and there was money available. So in fact, we then got into a whole phase of analysis and noise control. This was partly done by us, partly done by people at Stantec. It was a student project for a student working with me, that type of thing. We first of all started talking about concepts. You know, what sort of concept could we try and apply here to solve these problems? Well, with respect to the ventilation shafts there, we could possibly think of lining their internal surfaces, possibly hanging acoustical baffles inside the box so that sound going through is absorbed. The office partitions, we immediately thought of the idea of trying to install in those openings some sort of a Z-shaped acoustically lined duct that the sound and of course the air also had to flow through to get from the office, between the office and the corridor. Stantec was very, very concerned that we couldn't do anything to screw up the airflow. They actually did some internal modeling and imposed some constraints on the design of silencers that we wanted to do. They said that the baffles the baffles inside the ventilation shafts must not reduce the cross-sectional area more than 25%. And in the Z-shaped duct that we build inside the partition openings, the airflow lateral dimensions must always be at least 125 millimeters. So we respected that. We did an extensive ray tracing prediction analysis to design the silencers. I won't tell you anything about that. We were trying to achieve a sound isolation of sort of noise isolation class 35. Don't worry if you don't know what that means yet. Those of you in MEC 505 will soon. Okay, so what did we come up with as a solution? First of all, for the office partition, well, it's this Z-shaped crosstalk silencer. Okay, so that sort of shows it. Looking at the face of the opening, these partitions have been put in that have holes in them on one side at the bottom and holes in the top on the other side. So looking at the partition opening here in cross-section, you see you get this Z-shaped flow path we created with acoustical absorbing material, sound absorbing material on the sides to attenuate it. There's some pictures of it taken from inside one office and the outside. This was installed in one office. And of course we used green sound absorbing materials because all this was supposed to be really green stuff. In the ventilation shafts then, we did work with the concept of lining the shafts internally, also suspending baffles in them. We had occasion and money to treat 2 of the 4 shafts. On the first floor, we had lining and baffles together. On the second floor, we put in lining only, and we figured we could find the performance of baffles only by subtracting the second floor results from the first floor results. There's a sort of a picture of what the baffles looked like inside those boxes. And again, we use green cotton baffles. Okay, so what did this do? Well, with respect to the ventilation shafts, we managed to increase the noise isolation class by sort of 15 to 23 points to a values between about 39 and 56. We were trying to achieve 35, so in fact it was too effective, it was overkill, and the results suggested that possibly the baffles alone without the lining might be optimal. With respect to the partition opening line Z ducts, we increased the sound isolation by about 15 NIC points up to about 25. We still did not meet the 35 target we were trying to get. This worked, but it wasn't effective enough because apparently there just wasn't enough space to make these Z ducts long enough. With respect to airflow, the effect of these treatments on airflow, we called in our local expert, Karen, to come and do some evaluation here. And she can say more on that if she wants to, but my understanding was the conclusion we came to is we did not show that the treatments that we had installed had any effect on airflow, which sounds like good news, but we in fact think that it wasn't. There was no airflow before the treatment, so we couldn't screw it up after. So this is actually bad news. Would you agree, Karen? That's a synopsis? Okay. Okay, so that project finished, and then so there was a funny little project that happened right after that. UBC administration or plant operations, whatever, found out about the work in U and contacted us and said, hold on, there's a problem next door in Choi. Could we talk to you about that? So, of course, I and also Max Richter, the Stantec architect, got involved here. We looked around the building. We did some acoustical measurements and things like that. Provided as much advice as we could, and then the university said, thanks very much, and we didn't hear from them for a year. And then I happened to go back to the building, and lo and behold, I found out there were new acoustical treatments had been installed. No one had talked to me about it. No one had told me about it. So the problem then in the Choi building that relates to natural ventilation is again sort of these openings between the office corridor partitions and the steel deck ceilings. So again, these big openings that run along the top of partitions. That was the big problem. And we found out that, in fact, an acoustical consultant had been retained and brought in and had recommended putting sort of 1-inch, 25 millimeter thick glass fiber sound absorber against the steel deck ceiling across the partition, sort of going from in the offices to out in the corridor. So any sound that sort of went up and was trying to get through that opening had to bounce off that now sound absorptive ceiling. We thought that was neat. We didn't know whether it would be effective or not, but it was interesting that that's what the professional consultant had recommended. We thought we might try to find an opportunity to evaluate that treatment, and we did later. In any case, at the end of all this, 2 or 3 projects, 2 or 3 years, I came to the strong conclusion that what we really need to do, what someone really needs to do, what I really need to do, is sort of revisit the whole question of natural ventilation silencer design more scientifically as a sort of graduate research project. It's all well and fine doing short-term student projects and a bit of consulting, but let's do it properly. And so that then turned into the master's research project of Chris Bibby between 2009 and 2011. And there is no way that I can say what a great job he did, more than just to say it. Well, I can. Actually, I can tell you we're working on the 7th publication out of that master's degree. Okay, so I'm going to get into a bunch of math and things here. Bear with me. So one of the first things that Chris did is he proposed sort of a new theory for actually evaluating the performance of these silencers. And right from the start, it was the combined acoustical and airflow performance. And this was also intended to develop metrics which could be used for optimization. So he proposed a quantity called the open area ratio, OAR, which is the ratio of a the effective open area for airflow, fluids, F, to the effective open area for sound. The effective open area for fluid is the cross-sectional area of the opening times a thing called the discharge coefficient. Don't worry about that if you're not a mechanical engineer, neither am I. Divided by 0.61, and the EOAS is the transmission coefficient times the ventilator area. So this EOAF, the airflow metric, is based on the area of an orifice with a high Reynolds number, for which it's known that the discharge coefficient is 0.61. The EOAS is based on the area of a large orifice, for which the transmission coefficient is 1. Everything goes straight through. Of course, the acoustical performance varies with frequency, as always, and we had to give a lot of thought to how to deal with that. In the end, Chris argued that the way to deal with that would be to assume that the main sound we're trying to attenuate is human speech, and that, of course, it's always being listened to by a human ear. So in all of the work that comes from now on, we weighted the different frequencies by an A-weighted speech spectral weighting. And this is important that that choice was made. Okay, so the acoustical performance then is inversely proportional to this effective open area for sound. It's directly proportional to the effective open area for fluids. Now, that then we realize sort of is a way to quantify a given opening or silencer or anything. But Chris actually went further and he said, well, look, the way these things are defined conveniently, if we divide each of these, the fluids and the acoustics metric by the area of a cross-sectional area of the opening of the ventilator, SV, then we can define a thing called the specific equivalent open area for either flow or for sound. And the flow one is simply the discharge coefficient divided by 0.61. It's independent of area. The acoustics one is just related to the transmission coefficient, again, independent of area. So this actually quantifies the combined performance of these ventilators or silencers, whatever's in there, normalized to size, independent of size. So you can use this to scale the size up and down in order to get the performance if you want. Okay, so the whole idea was this open area ratio then is apparently very useful. It's a single number metric, just a number higher OAR indicates better combined performance. You can increase it by increasing the EOAF, in other words, the airflow performance, or decreasing the acoustical, decreasing EOAS, which means increasing the acoustical performance. For a large plane aperture, it has a value of 1, and it's directly related to common, often used metrics for airflow and acoustics. So apparently good stuff, right? You agree? Chris developed methods for measuring the performance, both acoustics and airflow and combined, of natural ventilation openings, both in a lab environment and in real buildings, as you'll see. This was based on sort of standardized techniques which are defined in lab standards, which basically involve 2 rooms with a partition with the opening in it between them. The acoustical measurement is based on ASTM E90 and E336, transmission loss. Put a loudspeaker in one room and make noise, see how much gets into the other room. And by the way, very importantly, this assumes a diffuse sound field. The airflow measurement is based on ASTM E779 and 1827. You use a blower door to blow air into one of the rooms and measure how fast it flows through the opening to the other one and what the pressure drop is across the opening. And this assumes a high Reynolds number. You want to know that if you're a mechanical engineer. These standardized methods were modified in order to essentially measure the leakage in the room, which is independent of the openings, so that it could be subtracted off the results where we did measurements of the openings plus the leakage to get the openings alone. And this then involved doing acoustical and airflow measurements with the opening we were studying both unblocked and blocked, as shown here. These pictures show this famous blower door. Complete coincidence, but I just picked this up from BCIT this morning for a student who wants to use it. It's sort of a membrane that fits in the doorway and has an opening for this big fan. The fan is calibrated for its airflow rates, and then you also have a manometer and pressure taps that allow you to measure the airflow across the test aperture. Don't worry if you don't really follow any of that. Okay, so we use these techniques then out in the field. We felt that was very important, see what the real world is like. In the end, Chris, we made measurements on 16 different ventilator type openings in 5 different buildings. These were organized in 6 different types. Type O, rectangular openings in medium partitions, like in the U building, in fact, in the U building, amongst others. Type R, slot openings next to reflective surfaces, like the one the acoustical consultant was concerned about in Choi. And then type A with an absorptive surface, the treatment that the consultant had recommended. Duct-like openings, like, where's that? Oops. D, here. Oh yeah, it's this thing up here, that's it. And crosstalk silencers, like we'd installed in U. And another thing we're becoming increasingly interested in is what is the effect of a grill that's been put on a ventilation opening, for example, in a door. There's lots of them around. Or sometimes they're above the door, like in Regent College here. Okay, there are the results. Got all that? I'll summarize what we learned from it later. So the other thing we did then is modified an office to turn it into a very simple 2-room transmission lab so that we could do controlled experiments in it. And this was created with the help of a French summer student. There's his picture. And this room is upstairs here on the 3rd floor. Okay, there it is sort of being built. There's the door that allows you to get from one side to the other. There's a test louver in position for testing. And we use this to do extensive tests on grills, non-acoustical type grills. The louver, which was just sort of a reference, because that's often sold as a sound attenuating silencer. Slot ventilators of various types with reflective and absorptive surfaces, again, simulating what the consultant had recommended in Choi. Crosstalk silencers of 3 different shapes, straight, there's my cursor, straight, L shape, and Z shape. And also, I'd been thinking about a sort of a novel way to try and attenuate the sound through these grills that are indoors in classrooms and things like that. So there's a prototype of a novel door vent silencer, which we tested. And there's the results. Good, eh? Okay, so I'll go on and I'll summarize later. Okay, so Chris also did extensive theoretical work in various ways, and I'll just try and give a bit of an overview of that and what some of the things we learned from it. Again, don't worry if you don't catch all the detail. He used simple diffuse field theory to predict how various parameters affect the speech privacy between 2 rooms separated by a partition with a natural ventilation opening in it. In particular, he was predicting a quantity called the speech intelligibility index, value between 0 and 1. The parameters he studied were the dimensions of the room, the surfaces that the rooms are made of, the background sound level in the room, the transmission loss of the partition in which an opening or silencer is installed, the transmission loss of the opening itself, with or without silencer, the opening size, etc., etc. This just shows one result, this graph, and it's essentially showing how, for 4 different partition types, how much the speech intelligibility index changes as a function of the effective open area of the ventilator, the opening in a partition, relative to that of the partition in which it is located. Okay, don't worry again if you don't get it all, but basically what you see is a lot of these curves are sort of separating once the value of the quantity on the horizontal axis starts to exceed 0.1 in most cases. And what we learned from that then was basically to avoid reducing privacy, the effective open area of the opening must not be greater than 10% of that of the partition in which it is located. And since the effective open area of a hole with nothing in it will definitely be much greater than 10% of that of a stud wall or whatever, you need a silencer. This sort of proved it. Okay, so that was sort of an important result here. In another phase of this theoretical work, he did theoretical modal analysis, predicting the fundamental mode attenuation rate of a lined duct in decibels per meter, and studying the effect of the duct aspect ratio, height to width, lateral dimensions, and the absorbent liner thickness. There's some results, and what we learned from this is, at least if you're assuming that everything should relate to speech and how humans hear it, so for A-weighted speech, then it appears that the optimal thickness of an absorbent lining on any sort of silencer is 50 millimeters. 25 is too little, 100 is overkill, 50 is optimal, so 2 inches. So that's important to know. Extensive work was done using numerical methods to predict the experimental results, in particular in the lab facility upstairs, to compare with experiments. Both acoustics and airflow. The acoustical performance was predicted by COMSOL finite elements, airflow by ANSYS fluent finite volumes. There's some nice pictures sort of showing you how the computer models were set up. One of the main things numerical methods were used for was to look at the performance of these proposed crosstalk silencers. We had come to the conclusion that they were potentially very effective on the basis of the little experimental work we'd done and also published literature. And using numerical methods, we studied 4 shape configurations: straight, L-shaped, U-shaped, and Z, and in each case for 4 different lengths of the airflow path through the silencer. Sorry, I'm not supposed to do that. Right, length of that path through there, either 30 centimeters, 50 centimeters, or a meter. And this was also modeling some configurations we had tested in the lab upstairs there. So just a few, well, 1 or 2 results here with respect to acoustical performance now. This is showing sort of acoustical performance of the 4 different shapes as a function of the path length on the left. The right-hand one is showing transmission loss as a function of frequency for the longest 1 meter long path length, the 4 different types. And what's interesting is that you don't see much difference between these 4 curves. And over here, if you look at how things vary with frequency and recognize that for A-weighted speech, it turns out the most important frequencies are 250, 500 hertz range. So down here, these curves are all identical. As long as you're dealing with A-weighted speech, the acoustical performance is essentially independent of shape. So putting elbows in, you might expect to attenuate noise. It does, but only at higher frequencies. So that was important to know. Airflow, well, here's a result. The SEOAF metric as a function of flow path length for 4 different silencer shapes. And what we see here is now airflow performance does very much depend on shape and also a little bit on length. The elbows increase the flow loss, but it's complicated. Maybe not surprisingly, there's more flow through the straight one, but surprisingly there was more flow through the U-shaped one, the red one, than through the L-shaped one. So the U-shaped one has 2 bends in it, the L only 1. We're not sure why, but the other interesting thing here is notice all these curves tend to rise a little bit. You'd think if you had a sort of a line duct or something, the longer it got, the more it would restrict airflow. Wrong. We were really surprised. It's the opposite. Increasing the length of these ducts actually increases the airflow. And that there's a mechanical engineering explanation for this to do with pressure recovery, et cetera, et cetera. So that was an important result. Look at the combined performance then, the open area ratio as a function of flow path length for the 4 different silencers, and we see that these can be very effective. Remember that OAR is 1 for basically just a simple rectangular opening. So the acoustical performance, or the EOAS, decreases, meaning the acoustical performance increases. The UAF increases, meaning the fluid airflow performance increases, both by increasing the length. So of course the combined measure OAR increases with an increased length, and the straight silencer appears to be the most effective. Okay, so we're learning a lot here. So let's put together all of these results. What have we learned from the field measurements? What have we learned from the measurements in the lab upstairs here? What have we learned from all this theoretical analysis? Well, here's some sort of key things. The acoustical and airflow performance of a rectangular ventilation opening in a thin partition is slightly better than the theoretical performance of a simple opening. The performance of a slot ventilator in a thin partition adjacent to a sound reflective surface is similar to the theoretical performance of a simple opening. Grills should be avoided at all cost. Right? At any given pressure differential across the grill, they reduce the airflow by half, by 50%, and they have no effect on sound. Okay, so double bad if you like. If you're trying to meet some ventilation requirement, what that means is you need to, if you put a grill in, you've got to make the opening twice as big to achieve the same airflow, and it has no effect on sound. So this is not good. Well, if you increase the size of the opening, of course, it'll let more sound through. The application of a sound-absorbing material to a surface adjacent and perpendicular to a slot ventilator, as recommended by the acoustical consultant in Choi, increases the acoustical performance about 3 to 6 STC points, sound transmission class points. It's sort of a frequency averaged attenuation there. So 3 to 6, not phenomenal, but better than a kick in the bum, so to speak, right? But it doesn't affect airflow, which is good. The combined performance goes up by about 3, or to about 3, so it seems to be good. Ventilation ducts have 50% greater airflow performance than a thin opening, and 3 times higher combined performance. So again, a big surprise, a duct, a long duct, allows more airflow through than just a thin partition. Surprise, but true. To attenuate A-weighted speech, the optimal thickness of an absorbent liner is 50 millimeters. Crosstalk silencers, we're right, they appear to be a good thing. Good acoustical performance, good airflow performance, so good combined performance. Cross-sectional shape influences airflow but not sound. Both influence with increase with the air path length. A Z-shaped silencer reduces sound transmission by at least STC 16. The flow rate decreases by 90%, but the combined performance is good with OAR values sort of in the 2.5 to 3.5 range. And apparently the straight configuration is best if you have the option. And happy news, my new little door opening silencer appears to work quite well too. Good sound attenuation, little airflow reduction, so good combined performance. Okay, so, you know, we've learned a lot, but let's just stop for a second and just remind ourselves of a couple of the assumptions that were made in all this work. When we did that, we realized this leads to some important ideas for things we perhaps need to do in the future. So on the airflow side, everything we did assumed a high Reynolds number, basically turbulent flow. That's because this blower door fan thing blows like crazy, and that's probably not very realistic. That's not what happens in the case of a real natural ventilation opening where the air just drifts through. So our results may not apply to the real life case that we're going to use these in. That's a problem. So we really need to investigate how to measure natural ventilation under more realistic conditions. That's a hard one. Then there's this assumption we made of A-weighted speech. That leads to the conclusion that the most important frequency bands, octave bands, are the 250 and 500 hertz values, so more or less low frequency. Is that correct? Is it speech that's the big problem in green buildings? I don't know. What we should do is a soundscape study in a number of naturally ventilated buildings to find out. And of course, at the end of all this, what we strongly felt was we've learned a lot, but what we've really got to do now is apply what we've done to the real world, get publications, of course, and then also apply it to the real world. Okay, so that brings us now to about 2013 and the CIRS Building on campus, Center for Interactive Research on Sustainability. This is a building that opened in September 2011. The building was designed to be the most sustainable building in North America. It is naturally ventilated in most of the building in good weather. And in September 2011, when it opened, I moved my office and my acoustics lab from this building over to CIRS for a number of complicated reasons, and started getting involved in life there. And it didn't take too long before the complaints about the acoustical environment started floating in through the natural ventilation opening in the partition between my office and my lab and everywhere else in the building. So the same problem we'd had in U and Choi and elsewhere, now I've got it in my own building on the partition of my own office. So that's great. I mean, that's good news because then I can apply what I've learned and actually fix some problems. So that led to 2 case studies in the summer of 2013. And the objective of those then were to sort of consider the particular situation and come up with an optimal cross-talk silencer design for acceptable performance. We had already installed the Z-shaped ones in U, so we decided that this time we'd do L and U-shaped ones. We did acoustical measurements and confirmed the poor performance leading to the complaints, found sort of STCs across partitions with the openings in them of 15 to 25, when ideally you want 35, and poor speech privacy, speech intelligibility index values sort of 0.4 to 0.6, where you want it to be less than 0.2. We established targets for ventilation and air and sound. So the ventilation fresh air ventilation target was about typically 10 liters per second per person. And we wanted to increase the sound isolation across the partitions by 10 to 15 STC points again. There was a fundamental problem, and there still is, and as you'll see in a minute, most of the partitions are mainly glass with a super fancy heavy door in, which is a total waste of money. So much sound just goes through the lightweight glass that there's only so much you can do by blocking the sound going through the opening. All right, so that was a problem we knew we'd have. So this led to 2 projects. One, an MEng project of a student, Mina Samimi. She studied my office. So there's the front, the partition of my office, all glass except for the door. And here's this huge, it's a 2-foot high, I guess, 60 centimeter high ventilation opening there with nothing in it. 0 privacy between my office and my lab beforehand. So she studied the concept of possibly extending the glass partition up a bit and then building a box around it, which created this sort of U-shaped silencer. And this was characterized by the length of the airflow path and the width of it, or the height, it's called here. I'm going to show you results for 5 different configurations. She tested more than that. Here's the sort of airflow and acoustical performance of the 5 different configurations separately. Again, I don't expect you to take that in. But what we found, or what she found, was the acoustical performance decreased with the height of the path, increased with its length. Airflow performance increased with the silencer height and length. Even for the best silencer, the airflow performance decreased by 70%, so that was a worry. But another student did some tracer gas measurements with Karen's help and found sort of 5.3 to 8.3 air changes per hour under normal conditions of just the window open and natural ventilation from that. And we had decided that 1.8 air changes per hour was sufficient, so it appeared that those airflow decreases weren't a problem. Combined performance then of the 5 configurations, there it is. Again, it increases with the length and maybe with the height of the configuration. The so-called 1.8 times 0.26 and 1.5 times 0.11 seem to have the similar best performance, but since that of the 1.5 0.11 was 30% more restrictive to flow, the other one was considered to be optimal. It had slightly better acoustical performance, which would give better speech privacy, which I demanded in my office. And so that was installed. And there it is. There's Mina up on the Genie building it in part. And it's still there, and all reports are that it works as it should. So that's good news. The second case study was on the other side of the building. It was a seminar room which is to be converted into a lunch room for staff in the building. Again, you can see there's the seminar room, glass partition here, wooden door opens, you don't see it, and this 2-foot high, 60-centimeter opening, which was going to lead to lots of acoustical problems. We decided, well, the student that did the work here was Kyle Harland, who we'd hired for the summer, and he is here. We decided we would work with the straight silencer here, and he tested a whole pile of different configurations. I've just shown 4 here. And same sort of thing, measure the acoustical and airflow performance of each. Acoustical performance decreases with height, increases with length. The sound attenuation provided by the so-called 0.14 by 0.75 seems to be similar to the blocked opening. We run into the limit of what we can do with sound transmitting through the glass. Airflow performance increases with length, decreases with height. Airflow was provided. The airflow provided by the best silencer, the 0.5 by 0.75 here, was about 25% higher than the original opening because we'd now created a duct. Tracer gas measurements again suggested that with the window open on a typical day, we'd have adequate ventilation, so that's good. Combined performance increased with the length of the silencer, decreased with its height. And with its excellent acoustical and combined performance, the 0.14 by 0.75 silencer was considered the best, since we wanted to make sure there was good fresh air ventilation in this room that was to become a lunchroom. So that was installed, and there it is, and there's Kyle at the top of the ladder working on that. So you can see the sound absorbing, the 50 millimeter sound absorbing lining there, quite prominent. So this I thought was really great. You know, we'd learned all this stuff and then we'd applied it in the real world. It happened to be my own real world, the CIRS building. We've, in my opinion, made that building greener and made my life better. It's a good news story. So where are we today and where are we going from here? Well, basically there's one last thing to do, I believe. And that turned into the master's research project of Vivek Shankar, which is nearing completion, and that is to look at configurations more where the original opening is actually pretty big and it's essentially already a duct, but of course never lined. So how can we attenuate the sound that gets through those? Here's an example in Regent College of a stack, what are those things called? In the ceiling. It's triangular shaped and stuff like that. Anyhow, so what has Vivek been doing? Well, he selected duct and baffle configurations. He's done extensive finite element method simulations, built what's called a surrogate model to try and generalize all those results. Pictures here sort of show some of the configuration that he's tested, either cross-sectional end shape, and the positions and numbers of baffles in the duct to find the optimal solutions. Then he essentially chose further ones for experimental verification. These are some of the ones that he's sort of moving on with. And last summer, we modified the room up on the third floor here extensively for his purposes. In particular, he wanted now the receiver room to be an anechoic chamber. And so he and I spent a lot of time sticking fuzz on the walls. And there's Vivek inside his new anechoic chamber. It's upstairs there if you want to see it. He is just on the verge of starting his experimental work. It's the same room as before, but modified, but also we're now considering it to be a scale model, probably not 1/8, but 1/4 scale model, so the rooms actually are equivalent to bigger rooms. That brings in a bunch of issues to do with scaling laws that have to be respected. And of course, he'll be using that to measure, again, different duct and baffle configurations, compare with his prediction, vary parameters to see how to optimize them, that type of thing. So he has to finish by this May. He's got a job starting on July 6th. Pressure. And I hope that'll be the end of this work. Probably won't. So that's the end of the seminar. And so all I need to do now is thank all of the various people who were involved, including Karen, who's here, and Kyle, who is here, and particularly Chris Bibby, who, as I said, did a fabulous job. He's now an acoustical consultant in Calgary. Thanks.
Any questions?
That was really fascinating, especially because I've seen a couple of the buildings that you worked on at the beginning, the Liu and the Choi. I love the idea of having the straight duct as being an easy and very useful solution. But the thing that I noticed with that copy room in CIRS is, first of all, the aesthetics of the baffling material. I wondered if you've had any comments about that. And second of all, I mean, you mentioned it was cotton. Is that right? And I wondered a bit, has Karen commented on whether that might be a host for organisms?
So, two things. First of all, these prototypes were never intended to be aesthetically acceptable. In fact, right from the start, we were very aware that our designs had to take aesthetics into account because no matter how good the acoustical or airflow performance was, if the architect didn't like it, it wasn't going to get installed. Having said that, we did get a couple of opinions on this, but it's known that that has to be done properly. These have sat in there since the summer of 2013. I'm a bit surprised. I would have hoped that CIRS would actually have them, if they want to keep them, rebuilt to look good, but they haven't. So I'm not sure what's going there. With respect to the sound-absorbing material, I'll hand over to Karen in a minute, but the generic problem here is that for eons, we have always used essentially fiberglass. And fiberglass is nasty in various ways. It's not considered green. This cotton product is specifically sold as a green sound-absorbing material, so I assume that Karen would be happy with it, but she may not have looked at it yet.
No, I haven't actually looked at that yet. And don't let it get wet. And the second item is if it's treated with an biocidal agent, in case it gets wet, don't breathe the air.
So the company that sells this is, it's called Acoustical Solutions. It's an American company. Go to their website to find out the answers to some of these things, like are they treated in a difficult way or not.
Hello.
Wally, hi.
So, the interventions that you did in the Liu and the Choi building, before that you did a survey that showed people are not happy with the acoustical condition. Then you did your intervention. I saw your NIC increase, but did you do another survey to see if that actually translates into occupant satisfaction?
We did not, but I can tell you that having finished the project, which installed a silencer in one office of Liu, we decided there was enough money left in the project to do a second one, and so one was done. A year or two later, when Chris Bibby expressed an interest in possibly doing his master's on this, I took him for a tour around the campus to show him what we'd done before, including Liu, and to our great surprise and delight, every office in the building had been done with the same silencer that we had designed. But no subsequent satisfaction surveys have not been done.
I'm just going to follow up on that survey question. It seemed from all of the buildings that you showed us, I mean, people are sort of consistently unhappy with both thermal control and acoustics. So I assume that the problems that you're seeing in these buildings are just problems that might be seen in all buildings?
Sure, you know, I could talk for 15 minutes about that, and I'd probably get Karen up to join me. Maybe the best thing to do is invite you to next week's, 2 weeks' time, Grand Rounds. Friday the 9th, is it, or 6th at 9:30, where Karen and I will be talking about a more recent study of a whole bunch of health authority office buildings. You know, what would I say to summarize in what I know about all this with respect to acoustics? Well, basically, every time you do a survey, people find acoustics unsatisfactory and the most unsatisfactory factor. Karen, you want to just say 10 words to generalize? What do we know about occupants' perception of whatever else? You know, it's complicated, but there are some trends, probably, I guess.
Yeah, well, it is complicated, and some of these factors relate to each other. But definitely, acoustics is it's difficult to control. You know, as we saw from this seminar, it's not easy to design a nice space that is also conforms to open plan office stuff like that. But the same holds true for air quality and for thermal comfort, is that if you're going to open everything up, that there are unique challenges. And I think that the design has preceded the science for being able to design good buildings.
Another interesting result that's come out of our latest study is that the occupant satisfaction survey, so what the occupants think of quality in various ways, does not always seem to jive with what physical measurements and comparing them to standards seem to suggest. That's an interesting one.
Okay, I think that wraps us up. In terms of thermal control, it's actually better in here than it usually is. So that's a nice thing. Thank